So the next half an hour, I would need to try to decide whether I want to give meta discussion of doing the overview of our overviews, or we just dive in and do sequential discussion of what is coming. What is coming is noise decoherence and error mitigation. So basically what we got is previous section translated superconducting physics and loops of those superconducting elements plus reception junctions. It translated that to second quantized Hamiltonians, which can allow us to see maybe the first approximation of not having a qubit. And when we drop those troubles, we get Pauli operators and artificial spins, which are our qubits. Okay. So we were able to see how we can try to make elements that couple qubits and so on. Yeah. So the next section in Spirit is asking, okay, how good will those qubits be? So we will be still in one leg in the kind of hardware, how it was fabricated. And with the other mindset, we will be saying, okay, how is it affecting this two-level approximation? That will be the noises. Okay, so if there's some charge noise on the superconductor, that will make the thing fluctuate in a weird way. Maybe we will decohere our qubit and so on. So that will be some ideas. As we are overviewing now, you see pictures of the block sphere, and we will start having some definitions of characteristic numbers that characterize the quality of the qubit. So T1 time and T2 time, or the dephasing times. So 1 page for some intro, 2 page for basically an overview how to capture what's going on with the qubit. Then there's a decoherence model, which will define for us those T1 and T2 times. I will zoom in because that's really something where you like, okay, I arrived at the milestone of my reading. Relaxation rate means that there is some sort of process. You can think of a Fermi golden rule, that there is some possibility of the qubit decaying into some environment. And that relaxation rate is related to how strongly you couple to the environment. And the inverse of that gives us characteristic times for the coherence of the qubit. We will be going more slowly, so we will understand what those times really mean. Yeah. If you look at this equation 44, you kind of see how it comes into play in the idealized model. So let me see if I can, sorry about this. Oh, what's going on? It's crashed or what's going on? Yeah, so here they are appearing. So on the diagonal, we have the longitudinal relaxation rate, I believe, longitudinal relaxation rate, and the off-diagonal elements of the density matrix will be the transversal relaxation rate. So we consistently use the same nomenclature as with the couplings. And we are assuming that we started from a pure state of a qubit in some composition of the superposition. So those alpha betas were coming here. We will get to this again, but yeah. So this is really key. If you don't follow the overview further, it's really essential that when you read, you at least read until then. And here it's nice because this will be based on some data, and then it's discussing in a very long way how to extract those relaxation rates from measurements of the experiment. If we get until here today, that will be probably meaning that I was too fast, but that's maybe one basic thing, that this can happen to an individual qubit. Just the qubit being embedded into physical environment, this can lead to those noises. So we want to go through all the nomenclature there and understand. Once you get this kind of stuff, there is a different type of noise, and that one usually is dubbed as difficult, because in regular electronics, this 1/f noise is usually something that you cannot very well control. There will be some discussion of more engineering. This section will be a little bit more difficult to understand maybe, but yeah, fine. And common examples of noise. Charge noise, those electrons are doing something. So maybe you get more charge into the system. Magnetic flux noise, maybe there's some impurities and they are talking to the system and coupling in a weird way. Okay, there is maybe an ensemble of this, so there's actually some spectral densities that might happen. Photon number fluctuations, that's actually a very interesting process. Yeah, so there will be maybe something going on in the cavity. So the cavity will be outcoupling somewhere into vacuum, or something else can happen. Everything can happen. You don't really know what's happening. Probably all of the bad things are happening and so on. That's fighting the noise. Quasi-particles. So there might be some dirt into the superconductor and there might be like some weird things going on and so on. Okay. So yeah, once you have this, so this is more or less a lot of text, you see, because there's maybe definitions. This is not really like it's really some derivations. There will be our discussion of those T-coherence models, those typical models. And then maybe you want to say that I want to model my quantum system by some operators. So that will be coming here, Fermi golden rule. I was right to mention that. You see, it becomes more technical, some integrals of some decay functions and so on. So it becomes a little bit like engineering. You try to fight the disturbing effects with kind of modeling that you know from engineering maybe. And then a discussion of kind of interventions in hardware that you can do. And then we will go to qubit control, and I want to go to this now, because that will connect to our coupling, and I find this relevant. So let me see. I want to just skip ahead to tell you that there's one thing that is relevant, because there's a big section that is in a similar spirit to what we gave up today. Okay. So this is a transmon with a capacitor, simple transmon. Now you couple in a time-dependent voltage, which is maybe some envelope like this. Okay. And now you want to model what's going on. So when you do this, this is coupling in some potential capacitivity. So it's a little bit like an oscillator that is driven in. And instead of having this additional oscillator, you take a semi-classical approximation, and instead of having a quantum variable here, you get a Hamiltonian. So if this would be an oscillator, you get an oscillator and a linear displacement operator. Okay. So this is a harmonic oscillator with a linear shift. Okay. And that's important because we didn't discuss how to control individual qubits. Okay. It's not connected to noise, which is the section that is coming up next, but that's kind of the point of this overview, that equation 75 connects to those capacitive couplings. That is kind of, if you continue with 75, you will understand the full control of the qubits. So once you have the qubits, you need to be able to reach all states on the Bloch sphere, and you need to be able to entangle qubits. Entangling qubits is what we just did with the capacitive coupling. And to control the qubits is this kind of figure number 12. Yeah, that's coming in a few sessions, but I will just follow the structure of the review and give the overview on how we model the qubits individually. So now the mindset should be that we forget everything about quantum computing that we wanted to do, and our only goal is to ask what's the quality of a single qubit somewhere in the universe. Okay, sorry, there's some oops. Okay. Okay, so no questions in chat, actually. Very good. So single qubit somewhere in the universe, how to check whether this qubit is not disturbed by the universe too much. That's what we mean by noise. the disturbance of the universe will be causing decoherence is a process where a pure state loses its purity and becomes a density matrix. Okay, the way you do it formally is actually by considering psi, which would be a density matrix, which is equal to its square. So if we have a pure state, that's the density matrix formalism. That's roughly kind of the math stat that will be appearing at some point. So, yeah, either you know about the decoherence already, or that's why the overview is meant to be complementary. Forget that you don't know all about this yet. Read through quickly, it's all text. It gives you different mechanisms that your superconductor might be suffering from, okay? So you'll just keep reading, and there might be systematic noise, stochastic noise, and different noise strengths, okay? So systematic noise, it means that basically the way you think you're operating the qubit is miscalibrated, let's say, okay? Which means it's something where you are not aware that you are doing wrong, but you're kind of doing that wrong, okay? That's a source of error, and that will be some noise that will be messing up the qubit. Another noise is, for example, thermal noise appears somewhere here, okay? And I'm not going to discuss this because it's just a block of text and you just read. You don't need to stop unless you are working on this. But if you're working on this, you will stop anyway. So you're safe. Noise strength and qubit susceptibility. Well, we will see what's going on once we get there. So yeah, that's one page where you can just, for Formula 1, just straight ahead and you go. Okay. Now the section B switches gears. Less text, maybe more formulas, and this should make you less uncomfortable about trying to understand what's going on when this noise is acting on my pure state of the system. So pure state of the system, it means that there's a wave function that we can consider, a E vector, okay? But as they will explain, at some point we need to go to a density matrix description of the qubit. So for a pure state, the density matrix of the qubit is something called the block sphere. So the block sphere is an angular parametrization of a 2x2 matrix, okay? And there will be certain components that will allow us to tune between a pure state and a non-pure state, okay? So a pure state, you can angularly depict like this, and then you see, okay, those are coordinates of a sphere. More or less, that's the idea, okay? So, yeah. Okay, so you just read through maybe a little bit of Wikipedia, you get the block sphere. Density matrix, one example of a density matrix is this. So rho is equal to psi psi. But you can also have rho is equal to 0, 0, A plus B, 1, 1. And that's a semi-classical state, more or less, because it doesn't have coherences. So when you have true superpositions, you will have also C, 0, 1, and plus Hermitian conjugate of such a term. Okay, that's why you have this kind of beta star here. And those 0, 1 are those two off-diagonal matrix elements, while A and B, A will be alpha squared. So that's kind of this. So this is this matrix element here. Okay, so I won't be discussing more because if you don't know this 2 qubits density matrix formalism, it's something you need to spend maybe half an hour on Wikipedia more to understand this. It will be a very pleasant read. Okay, so now the idea is that there is this Bloch-Redfield model of decoherence, which means that as time goes by, I have my time axis, the environment is kicking in onto the qubit, constantly pestering the qubit, and there's something going on with the qubit, okay? When the environment starts pestering a system which is in a pure state, then at time 0, so this is our time 0, we have rho 0, which is our initial state psi. But as time goes by, we have some density matrix. At all times, there is some density matrix that describes the qubit, but it becomes maybe different than our psi. Okay. And what might happen is that rho t squared might not anymore be rho t. So for rho of 0, you can check that psi is psi, but it might not be happening down the line. And this is called, I don't know, an entropy increasing process, because you can associate an entropy to this density matrix. So the entropy would be minus trace matrix log of rho. We had already logarithms in the bridging tutorial before. Okay, and we might see that this entropy might be increasing towards its maximum value as time goes on. That's more or less how physics will translate to the model using a density matrix, and might be going on for the qubit. Okay, so then they say there are those decay rates, relaxation rates. Why is it a relaxation? Because when we have an excitation in our superconducting loop, from the true ground state of the system, we might excite and change maybe some flux in the system, and we have this excitation that we put in, but that excitation might actually want to go away to the environment, and then the system will be left in its ground state 0, because it's so called dilution refrigeration. Okay, the review will actually tell you how people are cooling down the systems and so on. Okay, so that's why relaxation. Relaxation, maybe it means it goes down. Okay, now transverse relaxation rate is related to longitudinal relaxation rate. This is important. Okay, so there's some sort of Kirchhoff-like addition rules for the qubits. So transverse relaxation rate will be asking about how Rabi flopping of an X eigenstate is decaying over time. And because you might be pumping down, the environment might be just pushing the qubit back to the ground state, then of course plus will be eventually becoming 0, 0. Okay, because it will decay. So this first relaxation rate will also tell you about how coherent superpositions in the qubit are also decaying, but there might be something additional, which is called the pure dephasing rate, which is independent of just the qubit dropping down to 0. Okay, and they come in such a way that this sigma, okay, so I will clean up a little bit so it's clearer. Okay, so we only need to see here. So we have longitudinal transverse relaxation rate. So the transverse of diagonal elements of the density matrix in time. So there should be an element in time. That's what I meant by rho of time. The coherence model by Bloch and Redfield means that over time you expect that the density matrix of the qubit will be influenced by the initial pure state of the system, but there will be some non-trivial modulation, non-unitary modulation of those elements. So for example, the 0, 0 state will be 1 plus this. Okay, so what's going on here? Basically, this model is telling us that this will become small, which means the whole thing will become small, which means for t to infinity. So I'm now looking at the model limit rho of infinite time. this becomes small, I get 1. When this becomes large, this becomes small, so I get a 0. Okay. This is also becoming 0. This is also becoming 0. So rho of infinite time becomes 0, 0. So that's one limit case of this model. Okay. Let's say beta is equals to 0. If beta is equals to 0, then this is 1 and this is 0. So basically 0, 0 is called the steady state of this kind of noise. Okay. So if I start in 0, the noise will not excite the system back because this beta is anyway 0. So at all times, all those things in green are 0. So it will be a matrix 1, 0, 0, 0. Okay, that's another thing about the model, which means if you have incoherent initial conditions, then they stay. Okay. So what happens if I have alpha equals to 0 and beta equals to 1? Well, alpha is equals to 0. At time 0, this is 0. Beta is 1, but alpha is 0, so I don't have any coherence in the system. So basically, I will have a situation where 0, 1, this matrix goes to the steady state, which is this matrix. Okay? Because over time, this beta, which was initially 1, will become 0. And over time, this term here will become 0 as well. So the subtraction will not work anymore. And we will get 1. So it's just switching like this. Okay. So that happens if we have only this longitudinal initialization. If we have a non-trivial initialization, then basically what happens is that we both dephase away from the, so we remove the coherences. Those elements, those off-diagonal matrix elements are called coherences, and they start decaying. That's a bad thing because often we want to have a coherent superposition. Okay. So that's the Bloch-Redfield model. Okay. Question, I see a question for mixed states. I would need more info on the question. Okay, maybe it will come. So then you continue reading, probably it will tell you a bit more than I told you, but fine. Yeah. And then it's kind of splitting and discussing this longitudinal relaxation and off-diagonal relaxation. Okay. So good. So then you get an experimental challenge, namely if you start with Rabi flopping. Rabi flopping looks kind of like this here, that over time this oscillates, and you have this. So those kind of envelope fits of E2 minus alpha t, this will give us gamma I. And then you can discuss which kind of gamma it will give you, and then you're fitting and so on. Okay, so one challenge is how to take gamma 2 minus gamma 1 to get gamma phi, which is the pure dephasing. Okay. And that's discussed, and the way you do it is called Ramsey interferometry. If you will do more sophisticated pulsing, it will be called maybe the Hahn echo and so on. So basically what you do is you flip the qubit to start in some superposition, and then it's decaying over time, and you just read out. So basically you flip and you flip back and you ask, did I get the same thing? And you should get basically the same thing. And this is saying readout. We will go back exactly to this one, but I just wanted to show what I wasn't showing. Here they are explaining with pictures what this Bloch-Redfield model is doing. So if I start with an excitation, my steady state will be 0. If I start somewhere here and I didn't have longitudinal relaxation, then basically I could still have pure dephasing, which would randomize my state on the transversal plane. Okay, so I wouldn't lose maybe the excitation, but I would lose this phase coherence of the qubit. Okay, so you would get an ensemble of arrows on the transverse plane. Yeah, and note that this process can also, so if I would say my state is the average of pure states, which are those arrows, at some point they average out and you get basically an identity. Okay, so when the qubit starts getting mixed, it goes more or less towards the origin here. Yeah, so this kind of averaging might be an issue there. Yeah, so in reading, I really recommend to spend time, even if you know the block sphere, to compare the notations in the text and so on. That can take a bit of time. Okay, so this is this pure dephasing, and now the question is how to extract this parameter in the experiment and subtract out the longitudinal relaxation. Okay, and that's kind of discussed in the text here. I was reading through it. First time I was reading through it, I had a little bit of troubles that I'm not really so familiar, like juggling around Ramsey interferometry, Han echo. Here you have Han echo mentioned and so on. It was just fine enough for me to understand the basic ideas. What I was trying to do is, for example, make sure that the notation is straight, make sure that I can know what is actually being done. And if I would be running some numerics and so on, I would learn both more about it, but I would also do it more carefully, so you're fine. So there's those different levels of the detail of the reading that you might want to do. Having said that, not super easy. A lot of things that come in because it's different states for the initialization. Then the initialization might be doing something plus the environment acting on it. You assume you don't know the environment, so it's kind of something happening to the qubit, and then you get some data, and from this you interpret. So there's quite some stages of looking at the qubit. That makes the section a bit more complicated. So it's good to try to zoom out, and if some of the details are not missing, it might not be good enough to just go ahead. You might want to orient yourself around the figures and try to say, okay, so what was I doing? What was the protocol and so on? Okay, so a word of caution for this. But again, I mean, it's more or less as well written as it can get. It's just a bit of complication. So just maybe it's not a newspaper article where you just read through. You might need to spend a little bit of time and try to process, but it's possible. Using just a review, I think it's still possible. Yeah. And maybe a bit of Wikipedia here and there. Okay, so I would finish here, and then we will see if we go to more of those engineering problems that you know, the F noises and so on. Yeah, I think this is for now. Okay. Yeah. Okay. So good luck reading. Enjoy it. Remember that it's nice, and yeah, it's a lot of details in the noise sections, but it's really the make or break aspects of the qubits. So it's worth taking it serious and spend a few hours.